Okay, so we started talking the other day. Randomness, chaos, disorder. What is the symbol for entropy? All right, S, or really delta S, right? When we talk about the change in entropy, right? So it's a capital S. All right, and then what do we really look at when it comes to entropy? Okay, so how freely something moves. What else? I heard it is the randomness. How do we judge how random something is? States of matter, folks. That's what we're looking at here. Are the states of matter? Is that what you said, Lauren? Yeah, I just couldn't hear you. Absolutely. So it's the states of matter, guys. Which one has the most chaos? Why gases? They're the most spread out. What else? No definite volume and no definite shape. So they're the most random, guys. Lots and lots of chaos. That's a review from KMT. If you're confused about it, go back and watch the video from when we did KMT. Which one is the next most chaotic? Liquid. Why? They have no definite shape, but they do have a definite volume, right? And then the least is solid, right? Because they have what? Definite shape and definite volume, okay? So they're the most orderly, the most organized. You can see that just by their shapes, guys. They're very geometric, very concrete. You can easily measure their volumes. The other ones, it's very difficult to. So when we're talking about entropy, we're going to look at a reaction. Okay, we're going to have a reaction given to us, and we have to identify whether the reactions show an increase or decrease in entropy, in chaos, in disorder. So what do you think we're going to look at? Now, we can look at numbers. We're not doing any calculations with this here. What are we going to look at? The states of matter, absolutely. You're going to look and see what reactants I have and what do they become after the reaction happens. Does it become more or less chaotic? So let's take a look at number one here. What do I start with? A solid. And then I go to what? Solid plus a gas. So, what do you think's happening to the entropy? Solids, are they the most or least or in the middle? They're the least chaotic, and then we're going to a solid, which we said was the least, plus a gas. Well, what are gases? They're the most. So what's happening to our entropy, our randomness here? It's increasing, absolutely. Okay, so we're increasing our randomness or our disorder in this reaction. It's becoming more spread out, more chaotic. Take a look at number two. We're going from a liquid to a solid. What's happening to our entropy there? It's decreasing, right? Liquids have more randomness, and they're becoming more orderly and organized when they freeze, right? When that's freezing. Number three. What do you notice about number three? They're all what? Yeah, they're all gases. What can you tell me about gases, though? They're the most. Well, if I'm going from a gas to a gas, how do I know if it's more or less? Is there anything else I can look at? What's that?
Solution.
What do you mean by how many gases? Okay, so types of gases can be one way. What else is another way we can measure it?
Solution.
No, it's not solution because we're dealing with, well, I mean, they are a solution, but we're dealing with gases, so it's not about that. The number of moles, guys. So yeah, we have two different types of gases going into one here. They're reacting. But what we're really going to look at more than just that is we're going to look at the total number of moles. So on my reactant side of my reaction, how many moles do I have in total? How many? I don't hear anything. I hear mumbles. 4, right? Because it's just tricky. A lot of people say 3. Remember, if there's no coefficient, guys, written out in front, it's assumed to be 1. So 1 plus 3 is a total of 4. And how many do we have on the right? So what are we doing here? Are we going to a higher number or a lower number? What's happening to my entropy then? It's decreasing. I want you guys to go through and do your best to try and identify what's happening. Is it increasing, decreasing, or is something else going on here? Take a few minutes. Now, as you try these, what did you guys notice in some of these? Aqueous, right? We didn't talk about aqueous the other day or even today. But what do you guys know about aqueous? What are they like? They're like liquids, but are they the same?
No.
No, because what's different about them?
They're soluble.
Okay, so they have stuff that is soluble in the liquid, all right? Which means what? In terms of chaos or disorder? Is it more or less? Why do you say less, Ethan?
Well, it's like a solution.
It is, yep, it is a solution.
I thought that would be like less disorder.
Okay. Okay, since it's already mixed, so you're not doing the mixing. Okay, I can understand that. Sam, you say more disorder. Why? You just have a feeling? Just because in between liquid and solid? Liquid and gas? All right. Anybody else want to chime in with what they think? I'm not saying who's right or wrong just yet. Okay. What about them? What else? So something's already mixed together. Now I get that since you're not doing the mixing. Okay, it's already mixed. But a liquid is what, folks? And this is a review question. A liquid is, what is a solution? Let's start there. Forget about what a liquid is. What is a solution? It's a mixture, right? What type of mixture? Homogeneous, right? Or, yeah, well, it is homogeneous, right? So, a liquid, though, what's different about that? It's not a what? It's not a mixture. It's the same. It's pure. Okay? So, guys, think about it. If you take something and you mix it with, let's say, water, which was pure by itself, it was pure. Okay? If you mix something else, you introduce something else into that system, are you making more disorder or less disorder? There's going to be more chaos, right? Because you're introducing another piece into it. Now, I can totally understand, Ethan, what you were saying about how they're already mixed together. The mixing process obviously is going to definitely make you think, oh, it's more disorderly because you're mixing them together. But since they're already mixed, absolutely. But because we're introducing that in there, that we have two species kind of mixed together. You have water, potentially, as your solvent, mixed with a different solute. That's going to create more randomness or disorder. Okay? So, what I want us to do is off to the side, let's jot it down. Which is our least chaotic? Solid, right? Least chaotic, which is the most orderly. All right, solid is the least chaotic. And then what comes next? Liquid. Then comes what? Aqueous. And then comes gases. So aqueous solutions, guys, they're still sort of in that liquid phase. The particles aren't super far apart, but they can flow around each other and move a little bit more freely. So they are they're not as chaotic as gases, where they're just crazy. So, long story to get us back to right here with number 4. We go from a solid to aqueous. What's happening with my entropy? It's increasing. Number 5, solid to liquid is going to increase. Number 6, solid to gas. Increase. Now, side note, a little review. What is it called when you go directly from a solid to a gas? Sublimation. Good. What's the opposite of sublimation, where you go from a gas back to a solid? Deposition. Terms, folks, that we know: boiling, we know condensing, we know melting and freezing. Those are terms that we kind of tend to forget. But they're a review. We need to know those for our final. We will see those. Number 7, we go from aqueous to liquid. What's happening? It's decreasing. Any questions on those 7? All right, moving on. Number 8, solid plus a gas to a gas. What's happening to our entropy? It's increasing. Number 9, gas, gas, gas. What do we have to look at? Moles. How many moles do they have on the left? On the right? Oh, they're the same. So what's happening to our entropy here? Nothing, guys. It's remaining the same. Okay? It's neither getting more chaotic or less chaotic. It's just remaining the same. They're just being rearranged a little bit. Number 10, aqueous to solid is going to decrease. Number 11, what do I have to look at here? Moles. How many do I have on the left, Chase?
3.
On the left?
2.
2. On the right? 5. All right. Did I startle you there?
Yeah, you did.
Yeah, that's what I figured. What's happening here with my entropy? Increasing. Number 12, solid, solid, solid. Now this one, folks, you're not going to see this as much, to be honest. We're still going to follow that simple idea of looking at the number of moles. It's really not as simple as that. But for the sake of our notes right now, how many moles do I have on the left? 5 on the right. All right, so what's going to typically happen here? It's going to decrease. Number 13. What's happening? Decrease. Go from aqueous to liquid. 14, staying the same because we've got 2 moles on the left, we've got 2 moles on the right. And then number 15, decrease. Are there any questions? Number 8, what's your question with number 8? Oh, I'm sorry, what, we put increase there? Yes, we did. What's that? Okay. Why did you put decrease?